All right, so in this first video, the first thing we're going to write down is kind of what like a general shape of a graph looks like. So first is a constant function. You guys have seen this before. Constant function looks something like this. It's just going to be a horizontal line, and it could be through any y value at all, but it's just going to be a horizontal line. And we say constant, it means that the y value is constant the whole time. It never changes. Linear function looks something like this. It could have any slope, it could have any y-intercept, but the main point is it's a line that you could draw with a ruler. Like just a straight diagonal line. Okay, quadratic function. You guys have seen quadratics before as well. Those are parabolas. So they could be right side up, they could be upside down, but the parabola is going to look something like this. Okay, and it can take on many different shapes. It could be shifted up, down, left, right, flipped, but that's the basic shape of a quadratic. Okay, the basic shape of a cubic looks something like this. Kind of wiggles up and down. Like, see how the quadratic just goes down and then comes up, or it could go up and then come down. The cubic does like two little wiggles like that, like up, up, or if it's upside down, it could go down, up, down. The quartic, in case you haven't guessed, kind of adds one more wiggle to it. So it'll look something like this. So they almost take on this W type of shape, or again, it could be upside down. And then one more, the quintic function. Okay, so something like that. So it's almost like the number of directions you're headed in. So linear function is just headed in one direction. That's a power of 1. Quadratic is headed in two directions, down, then up. Cubic, up, up, that's 3. Quartic, down, up, that's 4. Quintic, down, up, down, that's 5. Okay, so basically tells you the number of little separate pieces, separate wiggles that the graph has. Okay, here's an important sentence that I don't want to get lost in here. The domain of any polynomial function is all real numbers, and then we'll talk about the range as our chapter moves on. All right, so end behavior, something that we're going to be working on is the behavior as x approaches infinity. Okay, the behavior of the graph as x approaches positive or negative infinity. Okay, the behavior of the graph as x approaches positive infinity. So here's what we mean by the behavior. On the ends, like this just goes up and up forever. This goes down and down forever. So these both go up forever. This goes up, this goes down forever. There are no more wiggles after the one that you've seen. So when we say end behavior, we mean like the direction it's headed out at the edges of the graph. Is it headed up forever or is it headed down forever? Okay, so we've got 4 different categories. An even degree, here's what I want you to look at. An even degree, these are the 2 examples that we have here. Notice that they are headed in the same direction. They either both go up, like these 2, or if I flipped it, they both go down. And that is dependent upon if you have a positive or negative leading coefficient. Okay, so quick example. Look something like this. Okay, so that's just an example. So here's what you write down. Okay, we've got these 2 different behaviors. Behavior number 1, we say that f of x approaches infinity as x approaches infinity. Meaning, the larger my x values get, the larger my y values get. That's all this means. They're both headed in a positive direction. And as I go off in a negative direction, to the left, as I go off to the left, my graph is just getting higher and higher. So we say my function approaches positive infinity, just growing without bound, as x approaches negative infinity, meaning as I go off to the left. So this is as I go off to the right, this is as I go off to the left, and this means that my graph is going up, and so does this. Okay, so my graph goes nowhere but up as we go off to the right. My graph goes nowhere but up as we go off to the left. That's what this notation means. Okay, if I get flipped upside down, I'm just going to keep with the simple one and do the quadratic again. Looks something like this. Okay, now these 2 things actually change to their opposite. In this case, f of x approaches negative infinity as x approaches infinity. So that means as my graph goes off to the right, my function goes nowhere but down. Okay, so as I go off to the right, my graph goes nowhere but down. And then we can say also goes to negative infinity as x approaches negative infinity. Meaning, as I go off to the left, again, my graph goes nowhere but down. Okay, so those are the evens. Let's look at the odds. The odds, notice they do the opposite thing. This side goes up, this side goes down. This side goes down, this side goes up. This side goes up, this side goes down. So we have one of each, and again, it depends on whether you have a positive or negative leading coefficient. We'll start with this one, because this one's right side up. So I'll again just do a cubic. Cubic is a nice, easy example. It'll look something like that. Okay, so as x grows, y grows. So that's this first statement here. So f of x approaches infinity, meaning it goes nowhere but up, as x goes off to infinity, meaning as the graph goes to the right. Okay, and then on the left side of my graph, I go down. As my x values go down, my y values go down. Okay, so as my graph goes off to the left, my y values go nowhere but down. Okay, and finally, if I have a negative leading coefficient, my graph is going to get flipped upside down, so it'll look something like that. And so I have the exact opposite pattern as I had right here. This time, on the right of the graph, my function is approaching negative infinity. It's going down as x approaches positive infinity. Again, translation, as I go off to the right, my graph goes nowhere but down. It'll never come back up again after these wiggles. And then f of x approaches positive infinity as x approaches negative infinity, meaning as I go off to the left. My graph goes nowhere but up. Okay, so those are the four different patterns you can see, okay? Even positive, up and up. Even negative, down and down. Odd positive, down and up. Odd negative, up and down. Okay, so those are the patterns. You guys are going to have those memorized eventually. Okay, let's look at these. Okay, here's the last little statement. Number of real zeros can be determined by examining its graph. Real zeros occur at x-intercepts. Okay, so the number of times the graph crosses the axis is the number of zeros. Okay, so here's what we want to do. For each one of these, describe the end behavior, which is basically just writing one of these four things that we have right here. Determine whether it represents an odd degree or an even degree, and state the number of real zeros. Okay, so this one. As I go off to the right, my graph goes nowhere but down. So I say that f of x approaches negative infinity as x approaches infinity. And as I go to the left, my graph goes nowhere but up. So we say the function goes up as my x values go off to the left. Okay? The fact that these are doing opposite things means I have an odd degree function. Okay? Odd degree functions go in opposite directions. And then finally, state the number of real zeros. I cross the x-axis 1, 2, 3 times. Okay, so the number of real zeros is 3. Okay, and let's look at this one. So off to the right, this one goes nowhere but down. So my function goes down as my x values go off to the right. And off to the left, same thing. My function goes down as my x values go off to the left. Okay, so that's the first part. Determine whether it represents an odd or an even degree. The fact that they're both going the same way means it's even. And finally, my x-intercepts, I have 1, 2, so that means I have 2 real zeros.